good morning or good afternoon, depending where you are, to everyone. As Arnie said, I'm a designer with ZOS Communications Server, and today we're going to be talking about ZOS V2R1 Communications Server and looking at an overview of the functions in there. As we move to the next chart, I will just briefly remind you of our social media presence. Many of you have heard us talk about this, and particularly me talk about it, so you're probably tired of hearing about it. And I realize that some of you are in organizations where you don't have ready access to these channels. But I do like to remind people that we're out there on Facebook, Twitter, and we have a blog. We've been much more active this year. We post probably 2 or 3 times a week on average, tech notes, presentations, other things, and I think we'll become even more active as we get near the announcement time for this release that we're discussing today. So just to let you know it's there. It is a good avenue of information. Having said that, the next chart is our usual disclaimer chart on the fact that this is pre-GA material. You see at the bottom of the page the timeline, and that still looks a little strange to me to see it with that gap there. We were used to that 1-year cadence for so long, and it seems like it's been a long time since we delivered a new function. So we're kind of excited about that, to be bringing V2R1 to you guys. The disclaimer says plans may change before GA. We have to say that at this time that is, of course, pretty unlikely. We are well into system test, well into beta test, but there could be a few tweaks here and there. So just remember, you're seeing a material here that's before the announcement and certainly before GA, so some small changes could occur. Okay, and here's the agenda. As you see, it's broken into thematic areas. That probably doesn't mean that much. We'll just basically be going through the function in some reasonable order. I'm going to start with a brief discussion of our requirement process. There's a few things I want to say about that. We will not discuss everything today. If you noticed in the last bullet on the appendix, there's an appendix, and I moved a number of smaller functions into the appendix, some stuff that I did not want to take the time to talk about during this hour and a half. You can read those on your own. We'll move on into the requirements section. You've probably seen a chart like this in the past. We often open our release overviews with this because our point is to try to tell you, you're going to see all this material and you might ask the question, why did we choose these particular items instead of something else? And this chart attempts to say, well, what do we look at to decide what we need in a given release? V2R1's going to be available soon. As you might guess, we are well into working on the release that's going to come after that. How do we determine what items to put into there? So this breaks that down. As you see, there are about 6 major bullets on here with some of the things we have to consider. First and foremost, System Z technology and the involvement of a platform. So this should be no surprise. If System C says jump, we say how high. We're always going to answer to the platform and do things that we need in support of the hardware. Secondly, many of you constantly remind us that we're not necessarily the most consumable platform out there. So we have initiatives related to simplicity, trying to improve the way you define our configuration and make it simpler. Security has always been a big part of Comm Server and will probably always will be. Every time you see a release overview, you can count on a number of charts being related to security topics. You will see that today to be the case. Performance. We always have a fairly significant focus on that. You will see that with V2R1, and I think again you'll continue to see that kind of thing in the future. The last bullet on the chart specifically talks to IPv6, but I would say we could broaden that and just say standards in general. Certainly as IPv6 evolves, as security standards evolve, it's not really an option for us. We have to be compliant with those. So that's always going to be a significant thing to understand with any release we put out, is what do we need to do to remain compliant. Okay, having addressed those 6 bullets, there's actually a bullet that's missing here, and that bullet is the issue of customer requirements. Going into any releases, we're laying out a plan. We look through the customer requirements, and it's very much a goal to try to satisfy as many of those as we can. How do we get customer requirements? The next chart talks to that. Some of you may have remembered the tool we used to use, FITS, and parts of IBM still use it. ZOS in Poughkeepsie still uses it. We have moved to a different tool called Rational Request for Enhancements. We've been on it now for a little over a year, and many of our CAP customers were some of the first people to exploit it. The great thing about RFE, I'll let you read all the bullets on here. I don't want to spend a lot of time on this, but the great thing about this is it's a web-based tool that everyone can get to. You no longer have to go through level 2 or an IBM rep. You can open a requirement. You can go to the URL that you see at the bottom of the screen right now, or from your smartphone you can scan the QR code and get there. Whatever, either way, you get into the RFE website, you submit a requirement, you can view requirements that other customers have submitted, and you can vote on them. We can interact with you. If you look at the bottom of the screen now, this is kind of the flow, and you'll notice that there's a phase there where we consider it to be under consideration. We might say, well, we need more information, and that basically returns it to you, and you can help us understand what it is exactly you're trying to ask for here. So it's a more interactive thing, and again, it just cuts out the middleman. So our success with this so far, we've been fairly pleased, and we continue to want to see more customer involvement with it. The next chart has a few tips. In the interest of time, I really only want to talk to the first one, which is that when you write a requirement for us, what we would like to see is that you address the problem that you would like to get solved, not just jump to the solution. Too many times requirements come in, and the requirement's written in the form of, we'd like to see you implement widget X, we want a knob for this, we want whatever. What we would really like to do is understand your problem, because in understanding the problem, we can then possibly suggest a more cost-efficient way to solve it, either from our own coding perspective, or possibly even with something we already have implemented that you could do right away rather than wait on us to solve your requirement through code in a new release. But in general, my message to customers is when they submit an RFE, it is very helpful to us and to the process if they've explained very clearly what the problem is they're trying to solve, and let us help them figure out what the best requirement would be to address that. Alright, I know everybody wants to hear about V2R1, so let's begin to move into that. The first themed area says economics and platform efficiency. With the exception of the first chart in this particular section, all of this will be related to performance and how what we do in V2R1 from a performance standpoint. So the first chart is probably the least exciting chart in the entire deck. It's the removal of bind DNS. Hopefully this is not a surprise to any of our customers, and certainly not to any of our CAP customers, because we've been advertising that this was coming for years. We issued an SOD way back in the V1R11 timeframe that said we would be removing bind in a future release. We updated it over 2 years ago to say that R13 would be the last release that includes bind DNS. The issue with it is that most of our customers do not run DNS on ZOS, and our particular implementation had gotten very far behind standards, and we were looking at a very substantial investment to bring it up to currency, and it did not seem, given the usage that we have for that function on the platform, to be a good business investment. So we have decided to remove it, and indeed it is no longer in V2R1. The next chart talks to enhanced fast path sockets, and the diagram you see on the screen right now is the standard TCPIP layers that a socket application would go through in sending data over the network. So nothing unusual here. You've probably seen these pictures before. The one thing that's interesting to note about this is when it gets to the point where we have to suspend to wait on a network flow to complete, the way we do that in the standard path is to invoke Unix System Services suspend resume functions. And that's all well and good. It works. We're fully POSIX compliant. The only thing is that we have to space switch into the OMVS address space to pull that off. And doing that is expensive. It adds up. So several years ago, we implemented something called enhanced fast path sockets. Enhanced fast path sockets did a couple of things. If you look at the diagram and you compare the left diagram to the right diagram, you'll notice that on the right picture, the Unix System Services Logical File System, the LFS layer, is thinner. So FastPath sockets brought a more streamlined LFS, and that helped. But the really big difference with FastPath sockets was that we, TCPIP, implemented our own suspend resume services. So instead of the space switch into OMVS, we could call that whenever we had to wait for a network flow to complete. And that should help performance, was our whole plan. The downside to it was that by doing so, since USS was out of the picture, we lost support for Unix signals. Because of that, we could not implement this at a global level. It had to be something that was enabled by the application owner. An application owner had to look at his application and say, you know, I can live without signals just fine. Therefore, I'm going to use this ioctl to turn on FastPath support. with that being the case, a relatively small percentage of the applications out there were ever enabled for FastPath. And that's unfortunate because our internal tests had shown that FastPath sockets had a fairly significant performance benefit from a CPU perspective. So what we're going to do in V2R1 is make a change that will allow us to have FastPath sockets be the mode of operation for all TCPIP socket processing without enablement by the application. So if you look at this picture now, we've replaced that box on the right with new suspend resume services from USS. They've written these, and they're written in such a way that they run as an extension of our TCPIP stack, and we no longer have to space switch into the OMBS address space, but we still retain the ability to process Unix signals. And so we're back to being POSIX compliant. Without any enablement from an application owner, you will now in V2R1 have FastPath socket support, and that brings us some performance benefits. The chart you see next, and you'll note right away, let's point out that the upper right says preliminary results. This test run was from about a month and a half ago, and we still had at that point some more testing to do. But the point is, if you look at this graph, what it's showing is throughput and CPU utilization numbers comparing with FastPath and without. If you look at the leftmost set of bars, that's for a RR40 workload. What that means is that's an interactive workload, request response, with 40 TCP connections running. And if we note in that case, we see about a 12.5% improvement in throughput and a little better than a 20% reduction in CPU utilization at both the client and the server. And as you go across the chart, you can see the numbers for connect request response workloads, which is kind of like web traffic, and streaming. And those numbers are much more modest, but there's still some benefit there. So the point is here is this is a fairly significant benefit. Again, it's preliminary. You will, about a month and a half to 2 months after we become generally available, we will issue a performance report that'll have updated numbers, and that'll give you a better idea of what the real benefit is. To beat the social media drum again, if you're following us on Twitter and Facebook and such, as soon as that's available, I will announce it there, so you'll be able to see that's available, and you can look at these numbers then. But the point is, for right now, we're very optimistic about a substantial improvement for interactive workloads with enhanced FastPath sockets. Now remember, when we talk about something like a 20% CPU utilization reduction, we are talking about that as being relative to the network path. So when we talk about any transaction that goes all the way from the application to the endpoint, end to end, the networking path is always a relatively small percentage of that. Typically for interactive workloads, it's probably less than 10%. So this 20% reduction is a reduction of that 10% of the overall path. So let's keep that in perspective. But it's still a very worthwhile improvement. Okay, the next chart is also performance related, but for a more specific case. We're going to look at how TCP handles selective acknowledgement and package retransmission. Today, in V2R1 and before, if you have an application that's sending some data, and let's say he breaks it up into 5 packets, host A sends those 5 packets to host B, and somewhere along the line, packet 2 gets lost. What's going to happen with that? Well, as you probably know what happens, that host B is going to be ACKing the packets he has received so that host A can retransmit lost packets. And the way that works is when he receives packet 1, he ACKs packet 1. When he receives packet 3, remember packet 2 was lost, he ACKs packet 1 again, because what he is ACKing, what he's acknowledging, is the last packet he received in order. So in this case, he's going to ACK 4 times that he received packet 1 because he never saw that gap filled. So eventually, host A will resend the packets that he doesn't think is made it there, packets 2, 3, 4, and 5. So what's the bad news here? I mean, the good news is that everything eventually gets here. It does fix itself. We fill the gap, and that's good. The bad side is that the sender has to resend packets that didn't really need to be resent, which is overhead for him. The network has to carry those extra packets. The receiver has to process packets 3, 4, and 5 even though he's already received them before. So we're wasting cycles here. So beginning at 2.1, we use something called SAC, Selective Acknowledgement. So same picture, we're going to send 5 packets. Again, packet 2 is going to get lost. The difference now is that host B, when he acknowledges packet 1, he also includes some additional information that says, oh yeah, by the way, I also received packets 3 through 5. So now host A, when he retransmits, he only has to retransmit packet 2, the lost packet, which is clearly more efficient. Now this is based on standards. The second major bullet on the chart lists the two RFCs, 2018 and 3517, that governs the SAC standards. Now, if you know your RFC numbers, you know those are very old RFCs. I think the current RFC, the most recent one out there, is somewhere in the 6900 range. So you can tell these are very old. Most platforms already support SAC. So we negotiate SAC capability when the TCP connection comes up, but the reality of it is most partners support it. Whether or not it's enabled is another matter, but they do support it. This is more efficient, but only in networks that are experiencing some reasonable amount of packet loss. So what we've decided to do in 2.1 is this function is disabled. The default, as you see at the bottom of the screen, is no selective ACK. If you want to enable it, you would do so by specifying selective ACK on the TCP config statement in the TCPIP profile. And this is another place to look to that performance report when it comes out for some information on what the costs of SAC are and when you might want to enable it and not enable it. Again, if the network is performing well, if you don't have packet loss, SAC is just overhead that's not going to buy you anything. The next chart talks to enhanced protocol configuration options and some default setting changes. So basically what this gets into is the fact that the TCP protocol has a number of timers that it has to maintain for various things, such as when it's going to retransmit packets, when it can clean up a connection that's in the process of terminating. It has various internal controls over the amount of memory being used for buffers and so forth. The thing is, many of these timer values and buffer values and so forth are internal. They're not things you can influence through any configuration options, and we've had customer requirements over the years to externalize some of that. So we're doing that in V2R1. Another thing that we're doing while we're in the neighborhood is updating some of the defaults. Many of the defaults for these timer values and otherwise were chosen back when we rewrote the TCPIP stack back in the 1990s, and as you can imagine, the network fabric has changed a lot, hardware has changed a lot, application workloads have changed a lot, and so we've basically revisited some of the defaults and updated them. As you guys probably know, we don't make changes to defaults very often. In this case, these were things that we felt like were really out of line with best practice recommendations, and we wanted to update them. There are about 5 charts in the appendix that go through the various options here that we've added in the 2 or 3 that we've changed defaults on. So if you're interested in that, I encourage you to look at those. The truth is, most of you will probably not need to configure these things, but for the case that you might have to in the future, they will be there as a V2R1. The next chart is something that has been a fairly significant customer requirement. QDIO acceleration was introduced in V1R11. And it's a really nice concept because if you look at the top picture and compare it to the bottom picture, the idea is that if you're routing packets from adapter to QDIO adapter to QDIO adapter, say from an OSA to OSA or OSA to hypersockets, if that's the case, what we can do is push down enough routing information into the data link control layer to let the DLC layer do adapter to adapter routing without going up through the IP layer. So if you compare the pictures, you can see what happens. You basically end up bypassing the entire IP layer, and you can pretty much guess what the advantage of that is. You're going to burn less cycles. You're going to have improved latency, and so this is a good story. You might look at this and ask yourself, but I don't want to use System Z as a router, so why would I care about this? Well, there's one use case in particular that many of our customers do care about, and that's Sysplex Distributor. If you picture the stack on the left being a Sysplex Distributor box, that's exactly what it would be doing. It's doing that type of router, and typically it would be between 2 QDIO adapters, either OSA or hypersockets. So this has the potential to be a very, very nice performance benefit. The thing that has blocked it for many customers is the fact that we disable it if IP security is also specified in the TCPIP profile. So if you're doing any type of IP filtering, or if you're doing any type of IPsec, either one, in any way or capability, you have to specify that keyword in the profile. Then we issue an error message and say that QDIO acceleration is not supported with IP security. So that the advantages of this function are good, but it has been limited into as far as how many of our customers can implement it, because many use IP filtering. Maybe not quite as many with IPsec, but at least some level of IP filtering is very common. So in V2R1, we basically allow you to code those two keywords together now, QDIO accelerator and IP security, and we decide on a case-by-case basis whether or not we can allow the acceleration to occur. And the table that you see here kind of defines what the rules are. So let's just, rather than go through every row, let's just kind of jump to the next to last row, because that's one of the rows that says QDIO acceleration permitted. And notice what it's saying is that if the IP filter rules you have permit all routed traffic and do not require routed traffic to be logged, then we'll permit the acceleration. The whole question here is, do we need to go through the IP layer to look at IP filter rules? And in that case, we would not. Now, that still could be a little restrictive, but the most important row on this whole page is the very last one, because what this says is Sysplex distributor traffic is always forwarded now. If you enable QDIO accelerator in the TCPIP profile, regardless of the IP security setting, then SD traffic will be forwarded. Now, we do not have, I did not have a chart here to show performance numbers. We did not have the measurements when I pulled this together. What I will say is that back when we implemented this function in release 11, and we did some testing at the time, as I recall, OSA adapter to OSA adapter acceleration resulted in a CPU utilization reduction of around 35 to 40%, again, of the network portion. OSA to hypersockets adapter acceleration resulted in a CPU utilization improvement of around 60%. So you can see this is a very significant savings. Again, those are old numbers. That's R11. Hopefully by the time the performance report comes out shortly after GA, then we'll have some more updated numbers to say what it looks like in V2R1. But regardless, it should be a substantial performance improvement. Okay, new section, application middleware workload enablement. And with like one exception, everything in this section will be a new or changed network management interface. So these are enhancements primarily aimed at vendors of network management application. The first one is the real-time application control TCPIP trace NMI. That's kind of a mouthful, and you might say that sounds kind of familiar. And it sounds familiar because we've had for a number of years a real-time TCPIP trace NMI. The change here is that insertion of the words application controlled. The great thing about this one is that if you look down to this bullet under the second sub-bullet under the second major bullet, this supports multiple independent operations running concurrently with their own set of trace options. So you can have multiple network management applications independently setting entirely different filters. And those filters are set independently of any MVS console commands you might have issued or any options you've coded in the TCPIP profile. The application, the network management application, determines exactly what it wants to see. Does it want to see data trace on this port? Does it want to see IPsec data in the clear on a packet trace with these IP addresses? The application decides all that, and you could have multiple applications running independently setting these filters. So one thing you see too as you get toward the bottom of the chart here is that with this we've now added, and this was a customer requirement as well as a vendor requirement, the ability to see IPsec data in the clear on packet trace, to see data, ATTLS data in the clear on data trace. This is under RACF authorization, so assuming you have the right permissions there, you can now get that data in the clear. The next chart provides a picture of it, and there's some notes on the, if you have the PDF, there's some notes on the chart after that. I won't read those notes. I'll just kind of talk to this picture for a minute. So what you see in this particular picture is a set of network management applications on the right, and they're each independently setting filters. One of them may say, I want packet trace data for this set of IP addresses. Another one only wants data trace data for this set of ports. Maybe they're setting things that overlap or not. So you set the filters. Now in the TCPIP stack, as we're going about our normal business, whenever we get to a trace point where at least one of the network management applications would be interested in the data at this trace point, we will write that into a common trace collection buffer, and then we have a long-running SRB that copies those into the staging buffers associated with each of the applications, which they can then retrieve at their leisure. If they don't retrieve them fast enough, the buffer's circular, so things will get overwritten. But even in that, there's an improvement, because the application will be notified exactly how many records were lost and what the time span of the loss was. So this is a much better NMI all around as far as the capabilities, and many vendors have expressed interest in exploiting it in the future. I'll skip the next chart again. That's a few more bullets of detail on the picture. The next one, it's probably not quite accurate to call it a network management interface, but 2.1 is going to provide some new security user exits. And the driving force behind this were vendor requests, vendors that wanted to be able to do things with our FTP client that they could not do to date. Many of you are probably aware that our FTP server has long supported exits for further control of FTP server activity. There are, I believe, 6 exits. One of them is not particularly recommended anymore, but there are still 5 that are in use. There's never been an equivalent for the client. The client, as of pre-2.1 days, has no exits associated with it. So we've had requirements to say we would like the ability for the client to drive an exit where we can inspect the command that's about to flow to the server and change the operands, reject the command, or terminate the client if something really bad is happening. And we did not have that capability until 2.1. So if you look at 2.1, just kind of drop down to the picture at the bottom. If you look over at the server box, the ZOS FTP server box on the far right, you'll notice I've called out a couple of exit points, and in particular the one on the top, FTCHKCMD, the check command exit. This is a very highly used exit. A lot of customers do have that in use, and that gives the server a way when an FTP command comes in, the actual retrieve or store or pass V command, it can examine it and decide if there's something that it doesn't like about it. It can reject it, modify the arguments, whatever. What we've basically done is put that same capability into the client. So if you look over on the client side, there's a new exit point, EZA FCCMD, the command exit. When the client has done everything it's going to do and is getting ready to actually send the command up to the server, it's processed whatever the subcommand was, a get or a put. It's taken into account all the current configuration options, and it's ready to actually flow a command. It'll drive the exit. The exit can then reject the command, it can modify arguments, or it can ask that the client be terminated. So there's a fair amount of power in there. There's a second exit point that you see at the bottom, the reply exit, EZA FCREP. And it's a little more limited. All it's basically going to do is get driven with the reply lines coming back from the server, and it can look at the replies coming back and see if there's anything in there that's significant enough of concern that it would want to cause the client to be terminated. But taken together, these are a fairly powerful capability. The next NMI is an enhancement to an existing NMI, really, that was again a vendor request. And the purpose of this NMI is to be able to gather information about the configuration of our FTP daemon and our TN3270 server, look at that, and then do something with it. In the case of the particular vendor that requests this, I believe the purpose is to be able to look at all that and make best practice recommendations, point out to you that your FTP daemon is not conforming to best practices or whatever the case may be. If you're familiar with FTP and TN, you know there's a lot of knobs and controls associated with these things. In particular, FTP with the FTP.data search order and their start parameters and environment variables. If a network management application wanted to figure this out on its own, it has to look a lot of different places to try to figure out what's going on. Now we're providing an NMI that says, tell me all you know about the FTP daemon, and we feed back the exact configuration options that are in force at that point in time. Same for the TN3270 server. Here are the exact configuration options that are in force at the time of the call. We provide two ways to get this information. The existing TCPIP callable NMI has two new request types where the application can retrieve this, or you can just generate it through SMF records. It's another option, which is fairly easy to do as well. The next two charts are bullets, a lot of bullets of detail on how that works. I'm not going to go through this. I just want you to know this capability exists in case you come across a product that might be exploiting it. You can see what the usefulness of that would be. Okay, the next topic concerns policy-based routing. We shipped policy-based routing back in release 9, and what policy-based routing did for you was it gave you a way to control the selection of the outbound hop from System Z on something other than the usual destination IP address and subnet. So if you wanted to choose which hop to go out over based on protocol or port, or even something like time of day, you can do that by writing policy rules to choose which hop you want to use. And sort of the classic example that we've always used of PBR is this picture that you see at the bottom of this chart. So here's a picture where we say we could set up a policy-based routing rule that says I would like my enterprise extender traffic to all go over this interface and everything else to go over this other interface. So enterprise extender traffic is defined as being on ports 12,000 through 12,004. You can have a PBR rule that says for ports 12,000 through 12,004, use this particular interface. That's what PBR is all about. This is intellectually is a pretty interesting function. From an exploitation perspective, we have a couple of customers that think it's the greatest thing since sliced bread, and they have solutions that are very much dependent on it. Outside of that, it's not a particularly widespread use function. What have we done to it in V2R1? Well, one big simple change we've been able to for IPv6. And I say that sort of tongue-in-cheek because it was not a simple change. It obviously hit very hard at the whole premise of the function since it was routing related. But it was one of the last functions in COM server that had not been enabled for IPv6. In this presentation, I've spared you the usual charts talking about IPv4 address depletion and the oncoming train that is IPv6, but the reality of it is becoming more important. We began our migration to our enablement of the stack, I should say, to IPv6 way back in V1R4, which G8 in 2002, so over a decade ago we started this stuff. And across the next few releases after that, we put together a pretty good story on IPv6 compliance. And to this point in time, we really were only down to a couple of major functions left that had not been IPv6 enabled. And here you see one of those taken care of, and you're going to see another one in just a few more charts. Okay, availability. Couple of topics in here. We'll start with RPC bind recycle notification. If you're not familiar with RPC bind, it's a daemon we have running that allows an RPC server to register the ports that it can be contacted at, so that clients can contact the RPC bind server and say, how do I get to this particular application? So the classic exploiter of this is our own NFS, ZOS on System Z. And so if you look at the picture here, an NFS server might come up, and one of the first things it's going to do is to obtain a port that it can be contacted on. It then registers the port with the RPC bind server. So in this picture we see that it's got port 2049 and it's registered that with RPC bind. Now if there's an NFS client out in the network and he needs NFS services, he can go to the RPC bind server and say, give me a port number that I can contact NFS on. That happens, and then the NFS client now can contact the NFS server. Nice, simple, straightforward, right? The question that comes to mind is what happens when the RPC bind server goes down? It crashes, it's forced to be recycled, whatever the case may be. Well, you saw the port number that I had in the RPC bind server box evaporate, right? If the server's gone, that registration information's gone. So now what are you going to do? The problem is that if even when the RPC bind server comes back up, that port information is still not there anymore. So the NFS server needs to re-register it. Anybody using RPC bind from a server perspective needs to re-register its port information. There really is no good way to do that today other than to restart the NFS server itself, to bounce that server so that it gets a new port and re-registers it yet again. And of course, that's definitely an availability implication there, if you're actually having to bounce NFS just to get your port re-registered. So in 2.1, the change we've made is that the RPC bind server will now raise an ENF signal, an Event Notification Facility signal, whenever the RPC bind server is going down or it's being started. And that way the NFS server or any server can listen for that ENF, and if it sees it, say, oh, I've got to re-register my port now. And that's a much better availability story. So here in the picture you see the ENF signal get raised, the NFS server sees that, it re-registers its ports, and now we're good to go again. Now it's important to note this is an RPC bind function. There is an older daemon on COM server called PortMap, and PortMap has basically the same premise, to provide RPC clients with knowledge about where RPC services reside, but it's an older daemon. We only made this update for RPC bind itself, and so if you're still on PortMap, it's one of those things at some point in time you probably want to consider moving to RPC bind. RPC bind is also IPv6 enabled, which PortMap was not. We are not enhancing PortMap. It's still there, but we're not making any enhancements to it. The next topic, application instance DVIPA affinity support. This is an interesting topic, and I'm afraid it's very difficult to talk to without framing it in the discussion of a particular application exploitation. But we're going to have to do that in this case because any application exploitation has not been announced yet. So we're going to try to kind of look at generally what this will provide to exploiting applications. An application instance dynamic VIPA is a DVIPA that's defined dynamically to represent a particular application within the Sysplex. So in my picture here, I've got application A and application B, both on ZOS 1. When they come up, they can ask for a dynamic VIPA to be activated that represents them within the Sysplex. You define a VIPA range statement, and then you activate the VIPA either by binding to the DVIPA or by issuing a particular ioctl call or mod DVIPA utility to cause the creation of that dynamic VIPA. Either way, it gets created, and now it represents the application throughout the Sysplex. So the problem here can be is what if you have these applications binding to NAT or any, and somebody wants to contact them. If you look at this picture, I have two applications, A and B. Both are listing on port 5000, but they're bound to NAT or any, and that's the important thing here. By being bound to NAT or any, that means that they'll accept connections destined for any IP address. So they're listing on port 5000. So we have a client here in the network. He says, I want to connect to VIPA A, and I want to be connecting on port 5000. That connection comes in. When it gets to ZOS, the share port logic says, well, I've got two applications listing on the port 5000. They're both bound to NAT or any, so they can accept connections from any destined to any IP address. And so what's it going to do? Well, it might route to the one on the left, which appears to be what we intended, but it also might choose the one on the right. Remember, these are bound to NAT or any, so they can accept from any IP address. So this could be a problem or not. It probably depends upon the application, but clearly it's not what the client intended. V2R1 adds support for Affinity for application instance DVIPAs. The idea here is that when application A asks for that dynamic VIPA to be created, it says I want to create it with an affinity to my address space. So I want to create VIPA A, and I want it to be known that this maps into my address space. So now if the client connects in saying VIPA A port 5000, and once again we have two applications listening on port 5000 but bound to NAT or any, the share port logic has an additional step now. It looks at this table over here and says, well, this came in to VIPA A, and look, I have an entry that says VIPA A has an affinity with address space associated with Apple A, and so it will route directly to that particular application. So obviously this has application exploitation requirements. If an application wants to use this, it has to modify its dynamic VIPA creation to say I want to do this with affinity to my address space. And you might guess that this was probably a requirement from a a particular application, and that would be true. So stay tuned. Again, once an application has made an announcement in that space, it's something we probably would announce via our social media channels and eventually via other avenues. When I was talking about policy-based routing a few minutes ago, I pointed out that that was one of the last major functions that needed IPv6 enablement. Here's the other one, Sysplex-wide security associations. This has been around a long time for IPv4. Sysplex-wide security associations for IPv4 was implemented, I think, in V2R1. It's been at least that long. And the idea with SWASA, as we sometimes call it, is it's the merger of two technologies, dynamic VIPA and Sysplex distributor technology with IPsec. So you want to be able to do IPsec tunnels into the Sysplex. You would like to have the capability for those tunnels to move as your DVIPAs move. You would like to have the capability for your distributing stack to be able to negotiate the security association for those tunnels with the endpoint, and then have that same security association accessible from that eventual target stack. That's what SWASA gave you, and that's worked, for over 10 years now. We have customers using that, but again, it has been IPv4 only. And so in V2R1 we implement that now for IPv6 as well as IPv4. Simplification. If we were in an auditorium or a classroom, this is the place where I would ask for a show of hands for how many of you have used Configuration Assistant. That's not going to work too well over the phone. All I will say is, in general, when I go out now and talk to people, I find that a majority of our customers have used Config Assistant, and some use it daily, some have used it on a less wide-ranging scope. We shipped it a number of years ago as a Windows tool that was not officially supported. You downloaded it, you could use it. Beginning at R11, we shipped a version of it that was integrated with the ZOS management facility, ZOSMF. It was fully supported as part of ZOSMF, and we began to encourage people to use that version of it. And so that's definitely where the future is going. As a matter of fact, pretty much 2 years ago, we issued a statement of direction that said after R13 we would no longer provide the Windows-based downloadable version of Configuration Assistant. All CA functions would be through ZOSMF, and that is true. As of V2R1 now, Configuration Assistant is provided only as a part of ZOSMF. And in V2R1 we have put a substantial investment into Configuration Assistant. We basically completely rewrote it. It was based on an older technology called AUIML, Abstract User Interface Markup Language, and we rewrote it to use JavaScript and Dojo, which are the technologies used by ZOSMF as a whole. Now, why did we do this? Because it clearly was a huge job. Well, there were three real goals with this. One is to be on technologies consistent with ZOSMF. Since we're part of ZOSMF, that is somewhat important. More importantly, was to get a consistent look and feel with ZOSMF as a whole. And if you've been using Config Assistant on ZOSMF in R13 or before, when you see it on 2.1, you're going to see that right away. It looks much more like an integral part of ZOSMF and less like something you bolted onto the side of it. It's definitely a better experience. The third goal was to improve performance, because as part of the rewrite, not only do we have modern web technologies we're using here, but we restructured the distribution of function between the actual Config Assistant server and what's done in the client itself, the browser. And in doing that, we believed that we would get improved performance. And it turns out we greatly underestimated the performance benefits of this. We have seen substantial differences. It's something really, when you think about using a browser environment, I believe would be that visible to the eye. But if you actually run a demo now, you look at the R13 version of CA alongside the 2.1 version, and you click on one and you click on the other, you see a very real difference in the amount of time it takes to respond and repopulate the next panel and so forth. It's a substantial improvement that you will see once you've tried the 2.1 Config Assistant. Okay, the next chart, going way back to the beginning of the discussion, I talked about customer requirements. If we looked at all the functions that we're delivering in 2.1 on COM server, this easily wins the contest for the most interested customers. This has a very long list of interested parties on various requirements associated with it. What's the idea here is to check the TCPIP profile syntax before you officially apply any changes. So before you bring up an initial stack or before you do a very-obey of a new profile into state. So if you guys do this kind of stuff all the time, if you have an error in there and maybe you've got TCPIP up and running and you want to do a very-obey and you don't see the error until you do the very-obey, well, now you could be in a kind of a bad situation because you could have a partial profile that makes it into activation, and that could lead to some pretty strange results, and in the worst case scenario it could even be something bad enough that would cause an outage. So the idea, and again many customers asked for, was give us a way to syntax check the profile before we even attempt the activation. So V2R1 gives you a new command. You see it on the chart there, very TCPIP, syntax, and the name of the profile. Then you get out a couple of bookend messages telling you we're starting syntax check, and then when we finish it, and in the middle you would see any type of syntax error message you would have seen during very-obey processing or initial stack activation processing. So we'll let you now know what is not syntactically correct and fix that in a less urgent manner than you would do if you were under the fire of a production very-obey change. And the next chart has a few more notes on this. The great thing about this is you can run it on any stack that you have. It doesn't have to be on the one you're going to eventually apply the change to. If you have a development system and you want to run your syntax checks on the development system, that's perfectly fine. It does need to be at the same release level. And if you have system symbolics in use in your profile, then you have to think a little bit about how the resolution of that's going to work. But in general, you have a great deal of flexibility there. The bottom bullet of the page points out that there are no updates are actually applied to the active configuration. That's kind of the whole point here. You don't want to apply updates, you just want to see that they're syntactically correct. And the most important thing I can point out, though, is that as I've put a highlight up on the screen now, is this will only flag syntax errors, not semantic. So if you had a interface statement that defines a VIPA on it, and it's syntactically correct, we're not going to catch a problem with that statement. Now, what if that VIPA itself is not defined elsewhere in the profile like it needs to be in the home list? Well, that's a semantic error. That's not a syntactical error. So just want to point out that those types of things we can't catch. We're truly looking for syntactical errors with this type of processing. The next chart, another simplification step in 2.1, is the implementation of the IPv4 interface statement for hypersockets and static VIPAs. As I said earlier, way back in V1R4, we did our initial IPv6 stack implementation. And when we did that, we came up with this new interface statement to replace the old device link home model. And that was the way you defined IPv6 interfaces. That's the way it's always been. But when we did that, that was only for IPv6 interfaces. IPv4 interfaces you still defined according to the same old way. Device link home, maybe BSD routing params. In R10, we added the capability to define IPv4 QDIO network interfaces through the interface statement. Only again for QDIO interfaces. V2R1 extends that now to allow you to do it also for hypersockets and static VIPAs. So you see kind of a nice example there of an interface statement in the little yellow box, and it shows what that looks like. It also gives you a very nice way to define your source VIPA. Now, the bottom of the page points out that this still does not apply to the legacy DLCs, and realistically it may never apply to them. So this is another case why you might want to consider trying to migrate towards more modern DLCs if any of you are still using legacy DLCs like LCS and CLAW and so forth. The next chart is another customer requirement from quite a few places, because most of you guys are ZOS people, and some of you may do your own firewall configuration. Some of you may have some network engineers that do that, but you're probably very familiar with the problem of network engineers that don't want to open firewalls completely. They would like to open them for a very limited set of ports, and up until V2R1 there wasn't a great way to scope that down. FTP had some controls for which ports it uses and so forth, but in general you couldn't assume anything when we were using ephemeral ports. They would come out of the full ephemeral port range. 2.1 adds a new parameter, ephemeral ports, on both the TCP config and UDP config statements that allow you to say that I only want to use ephemeral ports from this particular range. So you can scope that down to a much smaller area if you want to, within reason. So this again is entirely for trying to ease some of the requirements on opening a lot of ports within firewalls. The next chart talks to simplification of transfers of data sets with FTP on ZOS. And what this kind of gets to is the fact that MVS data sets, as we all know, are fairly complicated beasts. I mean, first of all, you have a lot of different types. You have to know, are you talking about a sequential data set? Are you talking about a PDS? What's the logical record length? What's the record format? There's a lot of things you need to know if you're talking about an MVS data set. And so if you want to transfer, let's say you want to do a get, you want to get this MVS data set and pull it down to from the server to our ZOS client on another host. Well, you need to make sure you understand what the attributes of that file need to be. You may need to issue some loc-site commands to appropriately set those attributes. Then you've got to actually do the get of the file itself, or if it's a PDS, you might need to do an mget. There's a lot of things depending on the file type and the file attributes that you have to keep in mind as you're doing this transfer, whether it's a get or a put, whichever direction you're going. So in 2.1, we introduce a couple of new subcommands and one new command that are designed to try to simplify this picture in some cases. So there's a new command, xdss, and you don't really need to know much about this because it's not something you issue. It's something that flows between the client and the server, the FTP client and the FTP server, to learn the attributes of the remote data set. It gets issued because you, as the FTP user, issued an MVS get or an MVS put, which are two new subcommands that say I want to get this file from the remote host and bring it down to my host, and I want you to take care of all this stuff for me. I want you to figure out what the attributes are, and you do the setting of them for me. You do the transfer. You do it as you transfer all the elements if it's a PDS and so forth. So the next chart has a picture that may explain it a little better. Here you see a little terminal that says I'm going to issue an MVS get for a remote file, remote.dsn, that I want to put in a data set on my host called local.dsn. And so the flow kind of looks like what you see below. The client starts off by saying, okay, do I already have a file by that name? No. I'm going to send this new xdss command to the FTP server and say, I want you to tell me what you know about remote.dsn. The server collects the attributes and sends an xdss reply with those attributes. The client then can look at those and say, okay, I need to internally do the equivalent of loc-site for all these different attributes to get them set appropriately. Now I can issue the actual retrieve itself for the file or elements of the file to put those on my own host, and then the server sends that back. And of course you can flip this picture around if you're talking about a put instead of a get. There's also the capability to a reallocation, which says that when I issue that MVS get command, I can specify realloc on the command. And in doing so, what I'm telling the client is when you go off and get this file and pull it down, if you have a file by the same name on the client already, I want you to not just replace it, because replace it would imply you just overlay it, which wouldn't change the attributes. No, I want you to reallocate it, which means you get rid of the old one, set the attributes appropriately, and then pull down the new one. Now, as I said earlier, we always will have a significant security focus within Communication Server. So let's look at what we've done in 2.1. Last time I tried to do a survey at Share, which was about, I guess, a year and a half, 2 years ago, one of the questions I asked about was the amount of ATTLS use by our customers, and I think at that time we were up around the 80% of the respondees said they were using ATTLS for at least one application, and some of them were using it for multiple applications. So that's really great, and we shipped this back in release 7. It's been around a while, and it's now been very highly accepted and exploited. So most of you know what this is, so I won't go through all the different bullets on this chart, but just briefly for those that might not be as familiar with it, you can think about ATTLS as being a wrapper around System SSL that allows applications to get the benefit of TLS encryption for their traffic without having to do the heavy lifting themselves. They don't have to make any changes to use the System SSL APIs. Everything's handled transparently from the application's perspective. The way we know the ATTLS knows that encryption has to happen is through policy control. So you see the person sitting up at the terminal up here. She's configuring the ATTLS policy, which is going to tell us things like, based on this port, based on this job name, based on this time, whatever, we do want to encrypt or not. We don't want to encrypt a particular type of traffic. So regardless, ATTLS now is wrapped around System SSL and is handling all of that transparently for the application. So this is all great. It gives the ability to for System SSL and the things it's doing to evolve, for security compliance to evolve without any application changes. But what it means for Communication Server is there's sort of a tax we have to pay, because we are basically saying we're going to allow the application to do all this transparently, which means that anything System SSL changes, we have to be able to support the definition of those changes through our ATTLS policy. So in V2R1, we have a number of changes that are basically in that category. We would call them ATTLS currency changes, keeping currently with things System SSL has done. So for instance, the very top bullet talks to a renegotiation extension that actually System SSL implemented a couple of releases back, and we've had some informal support before, but now in 2.1 you will be able to select that you want to use that extension through our Configuration Assistant. In R13, System SSL implemented elliptic curve cryptography, 20 new ECC cipher suites, and you'll now be able, as a V2R1, to choose those suites as part of the Configuration Assistant ATTLS setup. And maybe most significantly, System SSL and V2R1 provided support for TLS version 1.2, and with that you pick up a number of new cipher suites. They also at the same time did support for Suite B cipher suites. And through Config Assistant now you'll be able to configure support for all of that. So that is a way that we keep ATTLS and the policy configuration of it current with changes System SSL has made. Now we've had enough of requirements from customers and vendors for TLS 1.2 support that we have already made that available in V1R13 via a couple of APARs that you'll see on the bottom of the chart. I believe these became available around sometime in the latter half of 2012. It's not quite as nice as what you'll get in V2R1. You can't configure it through the Config Assistant. You have to use some environment variable type things, environment file, but it does give you the capability if you absolutely must have TLS 1.2 support prior to 2.1. Several releases ago, I think it was release 10, we shipped something called the Defense Manager Daemon, which gave you the capability of doing dynamic defensive filtering. And this, I'm not really sure how many of our customers use it, but I always thought it was a very cool concept, because the idea was that you could have a security appliance that was sitting out there and was noting that there was something happening in the network that was not a good thing, that looked like a possible intrusion, and you could dynamically drop in a defensive filter rule into the stack. You see in the picture up here that someone issues an IPsec command. That could be a person, but it could also be coming from some kind of tool that issues it. That tells the DMD daemon to immediately drop in this filter that says or forces us to block traffic coming from that particular IP address or that particular subnet. That filter gets inserted at the very top of the filter list, so it's very dominant. The DMD filters, the defensive filters that you create, get hardened into a database so that if you restart, you pick them back up again. There's lots you can do with this. Defensive filters are defined to be running in one of two modes, either blocking mode, which is what I just said. They're there to block traffic that you think is suspicious. But there's also a mode of operation called simulate. And simulate mode says that you don't necessarily want to block yet, but you just want to issue a log record to syslog-d that says that if I was really blocking, here is a record, here's a packet that I would have blocked. Simulate mode gives you the capability to sort of test drive DMD, to say, well, if I had it in place across the period of time, here is the traffic that would have been blocked because DMD is sitting there doing its job. So that seemed like a good thing, and that's for a number of years. After we shipped DMD, we would tell customers, well, try it out in simulate mode first, and then you can go to blocking mode once you're comfortable with what it's doing for you. What our customers quickly told us was that's all well and good, But when we're logging all of these simulated blocks, we end up flooding syslog because there's so much activity going on that we're just writing constant messages in there. Now, if we're actually blocking traffic, then you can turn logging off, and so that's not too big a deal. But it basically defeated the whole purpose of having a simulator mode. So in 2.1, we've added a user-specified limit for the number of defensive filter messages that we write to syslog-d over a 5-minute time interval. So this gives you a way to run simulate mode, but only see a subset, initial subset of what you're getting, along with counts of what you're getting, so that you have a good idea of exactly what this would be doing if you had it in blocking mode, but without the potential to overwhelm syslog-d. Net access. Many of you probably use net access. We've had it a long time. The idea behind net access is you go into your TCPIP profile and you define these net access stanzas that define security zones. You can have a zone out in the network that's your intranet zone, a zone that's your internet zone, whatever. It's you give a name to this set of IP addresses that represent a zone that you could connect to or from. And then you permit individual users, either inbound or outbound, to individual zones that they're allowed to get to. So in the case of this diagram you see on this page, it shows the user ID bhacker up there trying to access the intranet security zone, and that looks like that was allowed. But then you see the longer line where he's trying to go through intranet to get to the research zone, and you see a symbol there saying, well, we're not going to allow that. So he's been permitted to one zone through the appropriate RACF resource profiles, but not others. Okay, so we've had this around a long time, no change there. One thing about the way this works is that when we need to determine whether a particular user ID has the rights to access a zone or not, we have to make a RACF call, or whatever security product you might be using. And when we do that, we cache the result so that we don't have to go back to the security product every time. Okay, so that's a performance advantage, right? Don't have to go back if you're going for the same user to the same zone. And that's the way that's always worked. Now consider that, but at the same time think about the fact that the security product, RACF, then whenever it gets this one of these calls, it creates a log string which you can use from an audit perspective. So it can see what user is trying to access what zone, and over time do some auditing based on that. Well, what our customers have told us is that yes, they like to use that for audit capabilities, but our caching was keeping them from being able to do that in a comprehensive manner. Since we're only calling RACF some of the time when we don't have something cached, they couldn't see the entire picture. So 2.1 adds a new parameter to net access to control the amount of caching we do. So if you look at this table, the very top row, the default for this function will be cache all, and that will be the same behavior as you've had in previous releases, which says that we call RACF the first time, but then if assuming that we were permitted access to the zone, we don't go back again. Cache permit is the next level down, and this says we're going to cache the call to RACF for permitted access, but not when it's denied. And then cache same, the third one on this chart, is similar to cache permit but goes a step further. It says we're going to cache just like we would cache permit, but we will not use the cache on subsequent calls unless it's the same exact user to the same IP address. Remember in the two above, when we're going to a particular zone, whether or not we utilize the cache is based on whether or not it's the same zone, not the same IP address. So the bottom one says even if it's the same zone, but it's a different IP address within the zone, then we want to go back to RACF. So this means that if you look over at the far right column, you can go down through there and see the effect on auditing behavior. But if you get to the bottom right corner, essentially it's telling you at this point you're essentially getting audit records or log strings for almost every attempt to access a zone, except for when it's a permit to the same exact IP address by the same user. So you have a fairly granular method of auditing. Now there was still a hole in all this, and the hole was that this log string that we passed to RACF that got written out included some useful information, but one piece of information that was pretty vital was missing, and that was the IP address that you're attempting to access within the zone. So in 2.1, all SAF calls made for net access include that IP address. FIPS 140 diagnostics. So ZSCOM server has FIPS 140 operational modes for its IKE daemon, its Network Security Services daemon, and for ATTLS. Beginning in 2.1, System SSL in FIPS 140 mode requires the use of ICSF. It's going to go through ICSF. It's not going to use any internal routines. It's not going to make any direct hardware calls. If System SSL is configured in FIPS 140 mode, ICSF must be there. Well, what that means, backing up, is that IKD, NSSD, and ATTLS also require ICSF if System SSL is configured in FIPS 140 mode, because they're going through System SSL. So we've added some error messages basically in 2.1 to indicate to you that there's ICSF status is that it's down, and therefore IKE daemon or NSS daemon cannot initialize because it would be pointless for them to do so. Or that during the installation of ATTLS groups, we're going to install them, but we can't activate them because they're not going to do you any good because ICSF is not active. So we're taking a little bit stronger steps to prevent IKD and NSSD from coming up if ICSF is not there, and also to issue appropriate error messages to let you know that is happening. So the key message here is 2.1, System SSL is in FIPS 140 mode. ICSF must be up not only for System SSL but for our functions that depend on it. Okay, getting close to the end here. Enterprise Extender and SNA, clearly in this day and time there's not as much investment in this area, but there are still some tactical enhancements, almost all and probably all, if I thought about it, based on customer requirements that have come in from EE users. EE is still very heavily used across the world, and so there's a lot of enhancements that people request as they go further along with their implementations. This chart we're on right now talks to a function called progressive mode ARB that was implemented in V2R1. And when we implemented it at the time, we had a fairly narrow view of why we were doing this. We kind of had a picture that we were trying to address a problem where we had several, say, distributed comm server instances running inside one physical piece of hardware. One big Intel box with several CS distributed instances. So that could be that box on the right there that you see with several end nodes inside of it. And we knew that when we had a case like that, the flow controller algorithm used by EE, used by HPR, that's adaptive rate-based flow control, could not guarantee consistent response times if that box became overwhelmed. Again, it's one hardware platform, or are there enough processors to service all these images and so forth. If not, and we started getting inconsistent response times from the box, the HPR algorithm would throttle the send rates down dramatically. So throughput between the two endpoints would begin to drop drastically, and that was not a good thing. And in fact, we also realized that while we were kind of aiming this at the distributed comm server model, that box on the right could just as well be a system Z with a lot of LPARs in it and maybe not enough headroom, right? If you've got a physical KEC with a bunch of LPARs and maybe you're running pretty high on CPU utilization, you can get yourself into the exact same problem. So we implemented progressive mode ARB to be a little less overreactive to these changes in response times, and to be able to not be so heavy-handed in the cutting of throughput in those situations. And it had to be negotiated with a partner. The way you defined it was via keyword called HPR ARB that you specified on a single PU, a switch PU in the switch major node, or on the group in the XCA major node, or on a model PU. Very limited where we let you do that, and that fit our picture of where we were going with this. We said, well, this is not something that's going to be used very often. It'll be used only in a very few simple cases. What we found going forward in time is that progressive mode ARB works fairly well in general. We haven't found many cases where it doesn't work better than responsive mode ARB anyway. It doesn't have to be a picture just like the one you see here, but it can be a pain to implement if you have to code it on every PU in your switch major node. So beginning in 2.1, we allow you to code it on the group statement in the switch major node, which of course then sifts down to all the underlying switch PUs, which gives you a way to implement it on a broader basis. And in general, our experience has been that that's a pretty good thing to do. Next chart, IPv6 support for the IP adder operand. When we implemented IPv6 support for EE back in V2R1 a long time ago, our belief at that time was that people using IPv6 would be very dependent on good host names and an effective DNS infrastructure, that they would not want to code IP addresses manually, such as the one you see in the picture here. So the EE implementation of IPv6 has always required that you define IPv6 endpoints using the host name operand, the host name in the start option, the host name on the switch PU, the host name in the XCA major node. Whatever, you had to use host name. The IP adder operand has always been an IPv4 only operand. It could only point to an IPv4 address. Well, we've had a number of customers that say for various reasons they really would prefer to be able to code their v6 addresses as IP addresses using IP adder. So we have finally enabled that in V2R1. I won't go through all of these. There's a new filter on the display EE command to allow you to identify all EE connections to a given partner CP name. This can be pretty useful in some diagnostic situations when connecting in an extended border node environments. There was enhancement to PS retry that you see on this page. Many of you may not even be familiar with that function or know what it is, but basically it's an HPR capability to look for alternate routes based on a timer every 5 minutes to look and see if there's a better route for your HPR pipes, every 10 minutes, every 20 minutes. This enhancement gives you a way to say, well, that timer stuff's great, but why don't you just go look for a new route whenever you see a local topology change? And by local topology change, I mean a new link comes up, an existing link goes away, a link changes characteristics and therefore changes weight. In one of those cases, there's probably a good chance that another route might be available that could be better. So why don't you trigger the PS retry function in that case without waiting on a timer to pop? So that's just what that gives you. And that's all I was planning to cover in today's session. Again, if we go into the appendix, I'm just going to very quickly step through these, just let you kind of know what's there, but I'll let you read them on your own. We have some other, what I would describe as miscellaneous items. Most of these fall in the category of what I would describe as RAS. They're reliability, availability, serviceability. They're improvements in messages that we put out in diagnostic cases. They're improvements in things we capture under the covers, like in internal mini traces and so forth, to try to reduce the likelihood of you needing a recreate for various things. And I think that's all I'll say about the miscellaneous items. There's one here about ICMP outbound flood prevention, which is just basically an internal protection mechanism to make sure we don't let CSM queues get really long for unpaced traffic, typically unpaced traffic. Things like TCP traffic and EE traffic are all paced by TCP and the RTP layers of our product. But there are things like ICMP and RAW and non-EE versions of UDP that don't have those same pacing mechanisms. So there's a potential, and we really haven't seen much of this in the field, but we know there's a potential there for long queues to build up. And this is just some additional protection that we've put in place for that. And the next 5 charts are all of those configuration options I said we now have in the TCPIP profile. And again, I'll let you read through those. A lot of detail here. I'll particularly point you to the last of the 5 though, because these are the 2 where we have existing parameters that we've changed defaults on. We think our defaults or changes are still fairly conservative, but you will see these 2 called out in the ZOS migration guide when you get a copy of the books for 2.1, because since we're changing defaults, you need to at least be aware of what we're doing here. And that's it. Here's a bunch of references, again pointing to some of our social media stuff, some other things as well. Thanks for listening to this overview of the new and improved capabilities of ZOS V2R1 Communications Server.